Hi, everyone. Thanks for having me today. Presenting to the West Coast from the East Coast is pretty special. Thanks, global pandemic, for making this possible. Today, I will ignite an idea, one that I recently developed for work. So for the next 4 minutes and 43 seconds or so, I'm going to tell you how you think about space travel, why you think about space travel like you do, and convince you that sometimes the best way to travel is on a spaghetti trajectory informed by math developed in the 1800s. When we think about traveling through the solar system, we think about circles and ellipses. Satellites orbit in circles. We travel to the moon in an ellipse. This is because these are the solutions to the simple two-body problem. But the solar system is not a two-body problem. Heck, going to the moon is a three-body problem. Earth, moon, rocket. But when we went to the moon, we had the computational power of a Fitbit. 7-year-olds doing algebra could have calculated our trajectory. This in-body problem is a short way of asking the long question, what is the future location of these n number of objects that are affected by each other's gravitational pull? Sometimes it looks like the image on the left. Solving this two-body problem is easy. Solving the three-body problem is so hard, it has taken mathematicians literal centuries to solve. This dapper mathematician, Henry Poincaré, asked the three-body question in the 1800s. Nowadays, we have lots of computing power, and we find that the solutions to the three-body problem are not circles and ellipses. Instead, the solutions look like spaghetti thrown on a wall, as seen here. And we find that the spaghetti tends towards meatballs of stability, which we call Lagrange points or L points. At an L point, the gravity is pulling equally from every direction, such that anything on an L point will remain still. This graphic expertly illustrates the 5 meatballs that exist around every pair of celestial bodies. So there are 5 L points when considering the Earth-Sun system, and another 5 in the Earth-Moon system, making 10 altogether. Sometimes in math, there's not just one answer. We've found that the three-body problem has families of answers, and we call those families manifolds. And whenever an object is on a manifold, it no longer needs to expend energy to move. An example, this convoluted yet effortless spaghetti trajectory seen on the left shows the James Webb Space Telescope approaching Earth-Sun L2. This satellite is still under construction, is the universe's most expensive doula. The solution set to the three-body problem is low energy and long distance manifold maneuvers in asteroids, as seen here. This is Oterma, surfing manifolds around Jupiter. The red line is a trajectory. To clean up that concept, let's look at this red trajectory. Notice the trajectory merges onto a blue family of orbits. This is known as a manifold tube. This blue manifold tube makes its way to an orbit around a fat space meatball. Let's look at our spaghetti from another angle. Here we have 2 celestial bodies, 2 L points labeled, and a meandering manifold tube. Notice this manifold is restricted by a light blue region and converges. This is going in and out. Now, there are separate manifold tubes which keep objects in orbit on the meatball itself. Here we see a snapshot of these meatballs around L points in the Earth-Moon system. So now we have trajectories, and they're taking us on stable manifolds to meatballs of stability with Lagrange point core, and unstable manifolds removing us. Cool math, bro. What do we do with it? Well, we tell NASA, and they plan missions. So the convincing took about a decade, but the first mission, the Genesis mission, took solar wind samples at Earth-Sun L1 back in 2001. Since then, the Chinese Chang'e communication satellite surfed to a manifold in L2. Now we can take these spaghetti manifolds and connect them to meatballs of stability. And we can take them around celestial bodies throughout the solar system, because hopping on stable manifolds and unstable manifolds enables low energy, long distance travel to our space neighbors. Thanks for sticking with me on this journey. I hope it was effortless, because apparently it wasn't for me. But I hope that you went away with thinking about more than just circles. Yay. Pause, I need to grab some water.
Give that lady a Nobel. Give her she needs a And Grammy for that.
That was the most leave it all on the field Sin talk that I think I've ever heard.
Sorry about the end there. I lost my voice almost entirely.
We got you. It was good.
Yeah, I think
cool.
You didn't breathe after about the fourth slide, so that last breath, which is amazing. Okay, so you have lots of really cool slides. So if you want to reference any one of those in your answer, just let me know, and I'll right back through it.
All right, so we can do the same thing with raised hands questions. Oh, it looks like there's a question in the chat. I'll read it. Sounds like you're saying orbits are subtly unstable with end bodies, and you can do subtle tweaks to find an unstable trajectory that takes you where you want to end up with very little energy?
Yeah, kind of, mostly. So orbits in themselves are kind of circular, but what we're seeing now is not necessarily circularness from an orbit. Instead, if we go to slide 18, Preston.
Slide 18.
Yep. So see how each of these bodies has a gravitational field around them? They're all each moving in time as well. So if you're a satellite and you're can be falling literally downhill in this, and as the bodies are moving, your downhill changes a whole bunch, and that's where the spaghetti trajectory looks like. So the stable and unstable is kind of odd nomenclature, but what it really means is if you're on a stable manifold, you're on a winding trajectory that's going to end you up in an orbit around an L point. Because it's stable and because it's taking you to one spot, we call it stable. However, conversely, for the unstable manifold, it's an orbit around an L point that you end up not being in orbit anymore. You end up on a trajectory on one of these manifolds. And you end back up not on an orbit around an L point. There's a lot of other math terms that I can throw out, but to keep it simple, that's going to be my answer. I hope I answered it.
Thank you. I don't know how you're even approaching these questions. So nice job. How about James?
James Heelan.
James Heelan.
Hey, Cameo, good to see you. I sent you a text about this already. I'm like really embarrassed that I have used the term Lagrange point for a long time now. I can tell the world that James Webb's going to go to L2, but no one has ever actually explained what that meant to me before.
Mm-hmm.
So I appreciate that a lot. I'm wondering how large is the point? Like, what's the size of this stable area?
It's not necessarily a discrete location or a discrete point. So it's not 1 meter, and then all of a sudden after that 1 meter, you fall down the gravitational well that is like the black hole of the sun or anything like that. What it is, however, is a change in the space-time around gravitational bodies such that at the hill, Preston, if you could pull up another slide for me. If you could pull up slide number 9.
I can do that.
Rock on. So what we'll see here, James, is that some of these locations, this 3-ish meter area, can be larger or smaller depending on what kind of L point you're at. That is to say, and as Preston will pull up soon, that 4 and 5, those L points, are at the tops of these mountains. So after they're 3 meters, they fall a lot more and a lot quicker. And so that's a much smaller area. But if you go over to, for example, 1, 2, or 3, you're no longer at the top of the hill. You're a bit more at the bottom of the hill. So that region that is your L point of stability is larger.
There's another question in the chat. Are Lagrange points truly points, or what volume do they have in practice?
Yeah, so this is kind of the same question that James was just getting at. And if you noticed, I avoided giving you any number. And that's because, again, these things are changing. It's all very determined on the sizes of the masses of the bodies in question, and how far away they are. In general, I could probably toss my house to a Lagrange point and it would stay perfectly stable. And that could happen in like the DC region if we're considering L1. I would have to go home and do some math. I mean, I'm actually wearing my pajama pants now for humor because we're on a Zoom call. But I'd have to do some back of the envelope calculations to give you the actual numbers for the L points around the Earth, Moon, or the Earth, Sun. But for now, I'm going to avoid numbers.
Awesome. Kenji.
So looking at this diagram, it looks like these L points are like saddle points. Is that the right way to think about them?
Yes.
Okay. And did you said the Webb telescope is going to be sort of like orbiting around an L point actually? Like was that what got out of that slide?
Yes, it will be orbiting around an L point. It's going to go out there and it will go onto a stable manifold so that it will orbit for much longer. What we can also do, and part of the interest of this talk, is there are some manifolds that take you out to L points that are semi-stable. That is to say that given enough time for the Genesis mission, for example, it took a manifold out to an L point. It went around 4 or 5 times. It took that about 2 years until it mediated itself off of the initial manifold onto a different manifold. That manifold was an unstable manifold. So it took the Genesis mission satellite back in towards the Earth.
Awesome.
Question from Jamie.
Oh, me. Yeah, great. This is all incredibly fascinating and way above my head, but the thing that it's like, I feel like it relates to for me is like 2 things. One is when you're a kid and you have that giant parachute thing and everybody's doing the parachute and there's balls on it and they all kind of like go around the parachute. That's one thing. And the other thing is if you have like a, what's it called? Like not a lever, but like a spinning wheel thing with an arm and then another arm attached to that arm, another arm attached to that arm, and they all can spin freely. And it sort of like moves like it's wild, unpredictable, but like, are these sort of like unpredictable from appearance physics things? Is that related to what's going on here with gravity and all that stuff?
Yes. So I'm not sure what the first thing you said was. I think there's too much of an age difference or location of growing up difference or something there. However, the second thing you said was, as mentioned by Jordan in the chat, a triple pendulum or a chaotic pendulum. In physics, we really like to look at these because they describe to us just how difficult it is to figure out what the location of objects will be, especially when we're considering 3 objects and more. We're not even going to get into the more situation here, but for the 3-body problem, even the restricted 3-body problem is very difficult to understand what the future location of the objects will be.
I also, by the way, love the idea that you could like do back of an envelope math on some of these questions and have any idea how to translate that. That's just mind-blowing for me. There's more, I think.
And final question from Chander.
Hi, thanks, Cameo. Very interesting presentation. So I have 2 questions. One, why are there 5 L points? Like, why not 7, 20? Like, what makes 5 the number? And then second, when you're planning trajectories, do you think about, the role dark energy plays or dark matter plays? Because we don't know much about them, so how do you put that in the equation?
Sure. So your first question I'm going to address first because it was first. Also, Preston, you might want to add the word physics there because it's a book. It's a really good one, but you're going to get a lot of results for book whenever you search 3-body problem. Answer to your first question with respect to why are there 5 points, this pretty coolly plays into something that Jamie was mentioning with respect to how it is that we know that these even exist. And some of these were known about before we understood the solution to the 3-body problem. Because if we isolate the solution set, that is to say, for example, Jamie's chaotic pendulum, that's restricted because they have to be on a bar. Some of these are a bit easier to find out. Why are there 5? Math told us that there was 5. We figured out that there was 5 in time, but we did figure out that there were some of them before we figured out others. The second question was dark energy and dark matter. So dark energy and dark matter, I'll address dark energy first, is acting on a scale so large that it doesn't affect us on our solar system level. If we were trying to, for example, plan a trajectory out to the most distant galaxies in the universe, we would have to present some kind of manifold approach for the galaxies themselves. However, dark energy is not our concern here. Dark matter, however, is an interesting one because it does act on the galactic scale, not just the cluster scale. However, that is not our concern either when identifying these trajectories, because the mass content contributed from dark matter in our solar system is also not large enough to affect the gravitational pull outside of the objects that we know exist in our solar system.
Thank you.
Yes, can we have a round of applause for Cameo for that amazing presentation?
Thanks, everyone. My apologies for losing my voice there.